So for lesson 3, we are actually taking the exponential functions and using them in ways that they're used in real life. So the ways this is mostly with science and but economics as well and business, and we call it exponential growth and decay. Okay, so there is a little bit of reading here. All right, so exponential growth and decay, what is it? Many real-world phenomena can be modeled by functions that describe how things grow or decay as time passes. Examples of such phenomena include the studies of populations, bacteria, radioactive substances, electricity, and temperature. So people actually do use this stuff in real life. Any quantity that grows or decays by a fixed percentage at regular intervals is said to possess exponential growth or exponential decay. Okay, so here are 2 examples of graphs. Now, looking at our graphs from yesterday, is this one descending or increasing? Descending. It's descending, and we call this exponential growth. This situation is called exponential decay going... Oh my gosh, I got them backwards. I was going to say, that doesn't make sense, huh? Decay is on the left, growth is on the right. I don't know. I know. Okay, here we go. So this one is descending, so it's called exponential decay. I don't know what happened there. And this one is increasing, so it's called exponential growth. When I copied the graphs on here, I must have gotten them backwards. Because, make sure you make that change so we don't get confused. Okay, how many of you guys have heard of half-life in science?
Half-life?
Half-life?
No.
Yeah? Okay, half-life is the time required for a substance to decay and fall to 1/2 of its initial value. Okay, and that's called the half-life. Radioisotopes of different elements have different half-lives. Okay, so what we are going to do, if you turn page, we're going straight into examples.
Why are we learning about the half-life?
Okay. Okay, so what we're going to be doing for these problems is the problem is going to give you a situation and give you a bunch of information, but then it's also going to list for you what each variable is and what the formula is. So all we have to do is take the information that we're given and plug it into the formula. Okay, so example number 1, when a plant or animal dies, it stops acquiring carbon-14 from the atmosphere. Carbon-14 decays over time with a half-life of 5,730 years. How much of a 10 milligram sample will remain after 22,920 years? Here's the formula. N equals N, and this is called not 0, but we call it naught. So N naught times 1/2 time over H. Okay, so N naught, or the N0 is the initial amount. N is the amount remaining, T is the time in years, and H is the half-life. Okay, so all we have to do now is plug it in. So, do I know what N is, the amount remaining? Wait a second, hold on. The question is, how much of a 10 milligram sample will remain after this amount of time? So, do I know how much time is remaining? No. So, we have N equals N naught, or N0, the initial amount. What was the initial amount? 10 milligrams, right? So 10 times 1/2 to the power of T, time in years, so that's the 22,920, over the half-life. The half-life is 5,730. Okay. All right. So now all we have to do is reduce this, simplify it as much as possible, and we're done. Okay, so we can cancel each of the zeros, right? So we are dividing 2,292 by 573. You may use a calculator on these so that we don't waste a lot of time. It's 4. Okay, so that actually reduces to 4. You can use a calculator though. Okay, so it comes out to 4. So this is the same as n equals 10 times 1/2 to the power of 4. So that is n equals, order of operations, 1/2 to the 4th power gives me 1/16. Okay, so this is 10 times 1/16. Can I reduce anything before I multiply? This is the same as 10/16, right? Okay, and how does this reduce? This is 10 times 1/16. This is the same as 10/1. So you're just multiplying across. Okay, what goes into both of these? 2. 2 goes into 10 5 times, and 2 goes into 16 8. So our answer is 5/8. The amount remaining. So how much left? So that would be 5/8 of a milligram. Was that your question? Yeah. So this is amount, so we're looking in milligrams. Number 2. One certain element decays over time with a half-life of 800 years. Use the formula to determine how many grams will remain after 3,200 years if 500 grams were present originally. Okay, so we don't know what y is. Y is what's left. Okay, so y equals A. A is the number of grams present originally. So how many grams were present originally? 500 grams. So this is 500 times 1/2. T is time in years that has passed. So that is 3,200.
Over 800.
Over 800, good. Half-life is 800. Okay, so this is a little bit easier work. The zeros cancel here. So 8 goes into 32 how many times? 4 times. This is 500 times 1/2 to the 4th power. It's not always going to come out as 4, okay? So this is the same as 500 times 1/16, which is 500/16. And let's actually do the multiplication or the division on that one. So 16 goes into 50 how many times?
No, 3.
It's 3. 16 goes into 500 3 times, which would be 1858, right?
Yeah.
No, 48. So that gives me 2, 16, 1, 0, and 16 goes into 40 twice, which gives me 32. Yeah, 0.25. Okay, so that is equal to 31.25 grams, right? So example 3, a radioactive gas radon has a half-life of approximately 3.5 days. About how much of a 300-gram sample will remain after 1 week? Remember, let's convert 1 week to days. Okay, so maybe let's do this one together.
Yeah.
Okay. Okay, 1 week is the same as how many days? 7 days, right? And instead of making 3.5, let's change that to 3.5. Okay. So then let's plug it in. Y equals, what's A? The number of grams present originally. 300. 1/2. T, time and days that has passed. So that is 7, right? Over, half-life is 3.5. Oh my gosh, this one's going to come nice. So this is Y equals 300 times 1/2. What's 7 divided by 3.5? 2. Okay, so this is Y equals 300 times 1/2, or no, 2 to the 1/2 squared is 1/4, right? So this is the same as 300 divided by 4, which, Louis, what did you get?
75.
75 what?
75.
75 grams.
You're welcome.
Okay, guys, these ions are ones that we made up, so I don't know. I know. So geekonium-25 decays using the formula A equals I times 2 to the negative T over H. I is the initial amount, T is time in years, H is half-life. Half-life of geekonium-25 is 2 years. Find out how much of a 240-gram sample remains after 4 years. So the formula is a little bit different. The idea is exactly the same. So we're going to plug it in. A equals, what was the initial amount? 240 times 2 to the negative T. So that is, no, that's the half-life. The time passed is 4. So negative 4 over the half-life, which is 2. So this is going to be A equals 240 times 2 to the negative 2, right? And we should know this by now. What is 2 to the negative 2? 1 over 4. So this is actually the exact same formula, but because it's a 2 instead of a 1/2, they make the T negative, but it's the exact same formula. So this is the same as 240 over 4, which gives me 60 what? Grams.
How do you know it's in
The initial is in grams, so whatever's left is in grams. It's just whatever you started with. Okay? Yeah, so do number 5 on your own. Okay, so boogonium decays using the formula A equals I times 2 to the negative T over H. Half-life of boogonium is 4 hours. How much of a 24-gram sample will remain after 6 hours? Okay, guys, so we don't know what A is. What's I? 24 times 2 to the negative 6 over 4. Okay, so that gives me 24 times 2 to the negative 3/2, right? Okay, so what does that make 2? So this is the same as 1 over 2 to the 3/2, right? It just goes down to the bottom. What's 3 divided by 2? Okay, 3 divided by 2 is the same as 1.5, right? Okay, so this is the same as 24 times 1 over 2 to the 1.5. It was a 4. I had accidentally written 4. It's really a 2. Okay, so 1/2 is between 1 and 2. So what I would do is I would find, because this is a multiple choice problem, I would find, so this is between 1 and 2. I would find what all of this is if the exponent was 1, what all of it is if the exponent was 2, and then we'll pick the answer that's in between those two answers. Does that make sense? Okay, so let's do 24 times 1/2 to the first power, which is just the same as 1/2, right? So this is 24 over 2, which gives me 12. Okay, or 24 times 1/2 to the second power, which is 24 over 4, which is equal to 6. So my answer is going to be in between 6 and 12. So what answer is between 6 and 12? C. So we can estimate too. We don't have to find the very, very, very exact. If you have a calculator, you can.
Why would you put...
Okay, number 6.
Or 640.
Yes. Uh-huh. Sure. Yeah, no problem. Okay, so then we get 8 times 80, which gives me 640. This one, yeah. Okay, so in this case, we knew what the end population was, but we didn't know what the initial was. So 4,000 equals y naught times 2 to the t, which was 4 years. So we divided both sides by 16 to get y naught equals 250 people. Okay, so this was a case in which we knew the final, but we didn't know the initial. So just make sure that you read the question carefully. Last one, number 8. Also a multiple choice. The number of people with a flu virus is growing exponentially with time as shown by the table below. Which multiple choice equation expresses the number of people n having the flu at any time x? So what we're looking for here is if we're growing exponentially with time, these are going to be our exponents. But we don't know what that base to the exponent is. Notice how in our growth problems we always have a base of something. The exponent here is time. They give us the time. 0 days, 1 day, 2 days. But we don't know what that base is. So we need to look at how fast the people are, the number of people is growing. What am I multiplying 3 by to get 600? Times 2. What about 600 to 1200? Also by 2. Okay, so my base is going to have a 2 in it. Okay, which one of these 4 answer choices does not have a base 2? B. Okay. Okay, now we want to look at what our initial is, because notice how in the growth formula, we're always multiplying 2 to the t by our initial value. What is our initial value in this one? 300. So which one does not have a base of 300? C. Okay, now so we're looking at between A and D here. What's the difference between these two? One's adding and one is multiplying. Have we ever added before?
No.
No, so what's my answer going to be?
D.
D.
Well, how would you solve it? Just like that?
That's all they want is the equation.